Okay, so this is the second video for chapter 23 where we have ray tracing diagrams and lenses and mirrors and stuff. So I think this one we're going to look at a couple different types of lens problems. So let's see, first we're going to look at this example, 23.9. So it says, what is the position and the size of the image of a 7.6 meter high flower, it looks like a sunflower, that's been placed 1 meter, so it's only 7.5 centimeters high, but it's placed 1 full meter or 100 centimeters away from the mirror. And the mirror looks like has a 50 millimeter focal, lens. The lens has a 50 millimeter focal length. So I think one thing we need to do is definitely be careful to maintain consistent units throughout. Um, But we can see that it looks like if you just do some ray tracing where you go a parallel through the focus, that goes down here, and then you go straight through the center of the mirror. It's hard to do with things like this. That's why ray tracing is not perfect, but it's pretty valuable in terms of developing intuition. I think that's the main important part. And I'm sure they'll ask us some stuff on the AP with some ray tracing probably. So anyway, that one, you can see that the image is down here. Let's put it in green. So it looks like the image looks like it's been inverted. It should be a real image though, because it's actually produced by the light rays. You can see that there's no dashed lines here indicating like a virtual image. So that's another clue, is that if the lines are dashed and they're not like the actual light rays, then you should be dashing them when you do a ray tracing diagram like the ones at the bottom of your reading guide, and also that would produce a virtual image. But anyway, I think we can just use the equation. So if you noted that the equation for lenses is just about the exact same thing as for mirrors, so we just say 1 over the distance to the image, which they were asking for from the equation, is 1 over the focal length, which they just told us this time. We don't have to worry about curvature, minus 1 over the distance to the object, which is wherever we put it, right? So what's that going to be? 1 over, they said the focal length was 50 millimeters. So 50 millimeters, let's go to centimeters. How about we do that? So that's 5 centimeters. And then where do we put the object? We said it's 1 meter away. So that's 100 centimeters, just to be consistent with our units. Could have just gone to meters or whatever, but let me get rid of this kitty. Say hello, kitty. Okay, so when we do that, let's see what we get. The book likes to make a common denominator here. I'm just going to type it in my calculator. I got 0.19. That's 1 over the distance to the image that we want. That's a d. So the distance to the image that we want will be 1 divided by that, which is about 5 point, how many significant figures? Let's look carefully. It looks like 2, 3, 3. So I got 5.26, so we'll go 5.3 centimeters. Did they want the magnification? I forget. They wanted the size and location. So we've got the location. For the size, we need the magnification. So let's do that in a different color. So magnification for a lens is also just about the exact same thing. It's this. So then we're going to say negative 5.3. And that was 100, right? So it looks like this flower is going to get shrunk quite a bit. It's going to be negative 0.0526. So that's like a 5% magnification factor, which you can see from our little ray tracing diagram that it went from big to much smaller. So that does make sense. And this negative also makes sense because it's inverted, right? So that also makes sense. Did we really answer size though? They asked for the size, not the magnification. So if we want the size, shouldn't we go like the size is just going to be like that magnification factor times the size of the object. So I'm going to say that the size is equal to negative 0.05. I guess we don't really need the negative either, but whatever. We'll keep it there to say it's inverted. Times, how big was the original object? 7.6. That's negative 0.40 centimeters. So it's, in other words, 40 centimeters, or excuse me, 0.4 centimeters, very small, but in the opposite direction, inverted. Okay, so there's one example with a converging lens. Let's look at another example. So here we have a converging lens. This time we're going to place the object at 10 centimeters. So I guess I'll do it in red. So 10 centimeters from the mirror that's converging. You can see both sides are concave. And, excuse me, convex, not concave. Both sides are convex. So we're going to say the focal length is pretty big this time, 15 centimeters. So the object is within the focal length. Let's see what happens this time. So let's just go and calculate it with the equation first, and then we'll maybe do a ray tracing diagram afterwards. So if we put 1 over the focal length minus 1 over the distance to the object, we get 1 over d sub I equals, I got negative 0.03 continuing, so d sub I is negative 30. Interesting, so we got a negative reading on that one. So since it's negative, that means it's going to be on this side. Okay, so let's do the other one now. Well, actually, does that mean it's going to be on that side? I guess I got ahead of myself. This isn't a mirror; it's a lens. So let's finish here. So let's do the magnification. So the magnification, what is that going to be? So that's going to be 30 then, negative over 10. So we're going to be positively magnified by a factor of 3. So that means the image is going to be upright, but where is it going to be located? So I think that we've got to be careful here. So the fact that we got negative, let's go back to that previous problem and just have a look at it. Notice its image was on the other side. Did we get a negative down here on that one? And you'll note that we got a positive on that one. So if you have a converging lens that you're working with and not a mirror, you got to be careful of the sign conventions. A converging lens generally, I mean, in normal circumstances, produces an image that's a real image on the opposite side of the mirror. So since we got a negative, and notice this one was shrunken down as well. So in our problem, we still have a converging lens, but we got negative for our answer. So instead of being on this side, that sign convention says that it's supposed to be on this side. So normally converging lenses produce real images over here, but this time I think since we were inside that focal length, it's going to do something unexpected. So I think instead we got a larger image that's right side up, but it's 30 centimeters like way out here, something like that. So let's see if we can do a ray tracing diagram, and we'll try. It's going to be hard on here, but let's try to do a ray tracing diagram and see if that's true. And I wonder, is that a virtual image or is that a real image? Well, the ray tracing diagram should help us figure that out. So let's see. So first, shouldn't we go from the object and just go straight in? That's usually what we do. So we go straight in, And what's going to happen, remember the converging lens is going to direct that through to the focal point through over this way. So you can already see that we predicted the image is going to be over here, so maybe that means we have to trace it back. So notice I'm doing a dashed line, because that's not really the real light ray, is it? It's just like its path if it had been continuing straight. Okay, so that's ray 1. Ray 2, if you remember, is like the opposite. So instead of going parallel through focal length, we go focal length. So something like this. We'll pretend it hits about, well, I kind of bent it there, didn't I? Let's try to do a better job. Yikes. So this one was like that, right? This one we're going to go focal length through the top. We'll pretend the mirror just extends up here. So pretend the mirror keeps going. And then that would turn it to parallel, right? Just like the inverse of what we just did a second ago. But once again, the image isn't over here. And you can note that these lines aren't even crossing each other, so there's no way that image is going to be over here. But you still have a chance of getting something that's virtual back here. And look at that. It looks like it's going to where we predicted it would be, right? And then let's just confirm that. So the last image, so we went parallel through focal point to parallel. And remember, the last one for lenses is you go right through the center. It's not for mirrors, it's just for lenses. So we're going to go from the top right through the center. And you can see that once again, are any of these three lines over here touching? No, it doesn't look like there's going to be any image formed, any real image formed on that side. But once again, if I trace this back, it looks like it's going to that place that the equations told us. So it does make sense. The ray tracing diagram did confirm what we got with the equations, so that's good. Okay, let's look at a diverging lens for a change. So this time they said we have a 25 centimeter focal length diverging lens, so somewhere over here at 25 centimeters, and somewhere over here we've got like f and f prime for the focal lengths. And it said this time we have a goal. We want to produce a virtual image that's 20 centimeters in front of the lens. So in front of would mean on this side. So we want to produce a virtual image that's over here. So I think that once again, the sign conventions come into play here. So if you've done the reading, you're going to understand that, well, at least a little bit, that diverging lenses, they usually produce virtual images, first of all. They can be made to produce real images, but they generally produce virtual images. And they usually produce them on the same side as the object. So this doesn't seem to have anything really tricky in it. So note, you can use that same equation you did for the converging lens, or you can use the the diverging lens variant of that, which is on page 651. It's kind of up to you. I'm going to try to just use the same old thing so that we don't have to remember multiple equations. So the diverging variant of that is a little bit different. It looks like this. So it's got a negative 1 over the focal length, and the things are moved around a little bit. But let's just try to use that original one and use it for a diverging lens and see if we can kind of make sense of it that way. It's up to you though. So notice, what are we searching for here? We're trying to figure out where to put the object. So we're trying to solve for g sub 0. We know where the image is, and we know the focal length of the mirror. So if you're using the converging lens equation, you've got to consider the focal length of the mirror to be negative because it's diverging. So the focal length is going to be negative this time. So we're going to have negative 1 divided by 25. And then the image we wanted to be located at 20 centimeters, so we're going to have 1 over 20 over here. Except this has to be negative 2, so we're going to change that to a plus, and that's because if we're thinking about it in terms of the converging lens, a converging lens, just like in this last problem we had here, if it's on the same side that you want your image to be, doesn't that mean that like the image thing is negative, just like in this one? So that's all consistent, isn't it? So even though that was a converging lens, we're using that same reasoning here, so it's going to be plus. So that does make sense, I think, actually. And then we can solve for the distance where we need to put our object. So 1 over d sub 0 is, let's just do this without a calculator this time if we can. So another way to do this besides your calculator is to make a common denominator. And we might have to do that in the AP exam, right? So common denominator of these is 100, right? To fix this one, wouldn't you have to say that's 4, like 4 over 4, and over here you'd have to go 5 over 5. So then you'd get negative 4 plus 5. There's how you can do that without a calculator. So that's really just 1, isn't it? 1/100th. We're in centimeters here, so in other words, d sub 0. If we flip that, that's just going to flip and become 100 centimeters, isn't it? So if we want our diverging lens to produce this virtual image right here inside the focal length, we're going to have to put that object 100 centimeters in front of the lens. So that object is going to have to be way out here. Now let's do a ray tracing diagram maybe, and we'll do our best and see what we can do. So 100 centimeters, so this was what, at 25, so 50. So we need our object to be like way, do a different color, way out here in order to get a virtual image right there. So I guess we can try to do a ray tracing diagram. Let's see what happens. So if we go with a ray straight at it, we'll pretend this mirror keeps going much bigger. Oh my gosh, it's getting sloppy, but that's okay. Straight through the center, yes. Okay. All right, so this guy hits the mirror. What's the diverging lens going to do? Isn't it going to send it out in a divergent manner? That's what it's going to do in a divergent lens. So then you'd have like a fake virtual light ray back down this way. Okay, and so we went parallel, and that sends it out. So in a diverging lens, the next thing you'd want to do is you'd want to like maybe go straight through the lens, just like a converging lens. So straight through the center. Let's see if I can do it. Yeah, that's tough. Okay, and then there's that one. And what else could we do if we wanted to do a little confirmation? I guess we could go... this one's always tough for a diverging lens, but we could go like... So the last one that you do, so we went parallel to out, and that would like go through that focal point. So the other thing that we have to do is direct a light ray through the other focal point. So we're gonna have to try to hit that other guy. That's gonna be really tough without a ruler. So let's try. I'll try it in a different color here. Let's go yellow. So we're gonna go from the top of this object and trying to target this guy over here. Now notice, when you do that, what's really going to happen is the diverging lens is not going to let you do that part. What it's going to let you do is it's going to become parallel. Notice, just like we did with the converging lens when it's like opposite, so this one was parallel and diverged, so this one's going to be like through that, well, it was like parallel and then it like diverged out where it goes back through that focal point. This one's going to like be trying to hit the other focal point, so this part's going to be parallel. So it's the opposite of what happened on that first ray. But anyway, so what you're actually going to have is this is the actual light ray. The path you thought it was going to take was going to go through that focal point. Remember, we have the focal point right here, F prime. So then if we trace this parallel part back,
we get um, the virtual image. So we can see that what we were saying is confirmed. That is exactly where we thought it was going to be, isn't it? So that's pretty neat. Hope you found that pretty helpful. Diverging lenses are a little tricky. I'm going to try to find a virtual image produced with a diverging lens. Otherwise, I'll try to buy one and we'll try to do one in class. But we'll see what happens. One thing to note is I really would like you to do exercise H and I. So I'm going to make them part of the assignment, and they'll be some of the first problems you do when you work on the assignment. So make sure you do those. And make sure you give your ray tracing diagrams at the end of the reading guide a decent amount of practice. Okay? Hope this was helpful. I'll see you next time.